guys. So today we're going to be talking about acids and bases, which includes learning about pH, how to calculate pH, and how to calculate the concentration of an acidic or basic solution, which we're going to use when we do a titration lab next week. But before we get into all those new formulas and the calculations we will be doing with them, I just want to quickly talk about what an acid or a base is and the differences between them. So both acids and bases are solutions of some sort of substance dissolved into water. So they're always aqueous solutions. And they, to us, acids are something that are going to taste sour or sharp. They're going to burn maybe if they get in your eye. Examples include lemon or other citrus fruits. Vinegar, coffee's acidic, tomatoes are acidic. Anything that's gonna burn really bad. A lot of things that burn badly when you have a cut or a cut in your mouth or something. But bases, on the other hand, actually are something that taste bitter. They often feel slippery. Examples include bleach, baking soda, ammonia, antacid. These are all common household examples of both acids and bases. You can find more of them in your book. Both acidic and basic solutions are going to conduct electricity, and we don't really learn too much about that this year, but if you take AP Chem or Chem in college, you will learn more about that and how it happens. Common examples are listed right here. These are some of the ones that are on the back of your periodic table. Here are some common bases. Just what you should recognize here is that all of our acids start with a hydrogen, 1 to 2 hydrogens in the front. And remember, that is how you identify one of our acids. If we see a hydrogen first, and we know that when that goes into water and it is dissolved in water, it dissociates in water, it is going to be considered an acid. Whereas our bases, besides our ammonia, we are going to have often an OH at the end. And that is our little hydroxide polyatomic anion. So that is our base right there. The definition that we are going to use for an acid is something that is going to produce hydrogen ions in a solution. That is why all of our acids have hydrogen ions at the beginning, because when these go into water, they break apart and form a lot of hydrogen ions floating around in our water. Bases, on the other hand, are something that is going to produce a lot of hydroxide ions in our solution. So remember, hydroxide is our OH minus. So you can see that over here we have our hydrogen plus for our acids, and our hydrogen ions for our acids, and our hydroxide ions are bases. Change in indicators, basically we are going to learn more about when we do our lab next week. You just need to write down that we have clear for our acids and our phenolphthalein is going to be pink for our bases. The pH range, which you probably learned about in middle school, for acids are going to be less than 7. And that is because our hydrogen ion concentration is going to be greater than our hydroxide ion concentration. Okay? And how we calculate the pH is actually just the negative log of the hydrogen ion concentration. Now, bases, on the other hand, have a pH greater than 7. And that is because the hydroxide concentration is larger than the hydrogen ion concentration, and our pH is our POH, this should say. Our POH for this is going to be equal to the negative log of the hydroxide ion concentration. So we're actually only going to be looking at and using this formula to calculate the pH, which we're going to learn about right now. So actually, to calculate pH, you just saw this formula. It's just the pH is equal to the negative log of our hydrogen concentration. So it's just our hydrogen ion concentration, which is just the molarity of hydrogen of our solution. Remember, you're probably wondering, pH, that sounds kind of familiar from middle school. Maybe Ms. Thomas or Ms. Frankovic have talked about it already this year. But pH is just a numeric scale that indicates how acidic or basic a solution is. So if something has a pH less than 7, it's considered acidic. If something has a pH of more than 7, it's considered basic. and things that have a pH of 7 are considered neutral. We will look at a few examples of different pHs of different substances in class, but you just need to remember that it is a numeric scale 1 to 14. Now, it is kind of like the Richter scale, where a small change in pH from, let's say, 7 to 6 is actually quite significant. It's like a greater magnitude than just 1, like we would think of something like the scale to be. It's actually, because of the logarithmic relationship, it's actually times 10. So just like a 7.0 earthquake is significantly stronger than a 6.0 earthquake, a slight change in pH, for example, of the ocean, actually has a really large impact on ocean ecosystems, which you read about in the 6th section. So usually when we're calculating pH, we have to find out what the concentration of hydrogen ions is, and the concentration of hydrogen ions is just the molarity of hydrogen ions. And you just need to be aware that strong acids are going to be they're going to completely dissociate in aqueous solutions to produce those hydrogen ions. So basically, we dissolve something, and those hydrogen ions are bopping around a lot. A weak acid is only going to produce a few hydrogen ions. Every example that we look at, both on here in class, on the final, are going to be examples of strong acids. That's all we're using right now this time. Okay, so our example that we are going to do helps us to calculate the pH of a solution. So our givens are basically just the molarity of the solution, or the concentration of hydrogen ions. So the instructions are to calculate the pH of a solution with a hydrogen ion concentration of 1.00 times 10 to the negative third molar. So what we have right here is our new formula that we learned, pH equals negative log of our hydrogen ion concentration. So I just plugged the molarity, or Emma's going to plug the molarity in right there, times 10 to the negative 3 molar. And you plug that into your calculator, and pH actually is going to be equal to 3. So, is this solution acidic or is it basic? If we go and we look at our two examples, pH is less than 7, it is acidic. So we have a acidic solution. That means that our concentration of hydrogen ions is greater than our concentration of hydroxide ions. And this is a pretty acidic solution. This one is one that we probably would not want to mess with. Okay. So, now that you guys know how to calculate the pH, we are also going to use the molarity, or the concentration of hydrogen ions, in acid-base reactions in our lab that we're going to do next week. So, in general, the reaction of an acid and a base is a double replacement reaction. Okay, it's also called a neutralization reaction when we're talking and referring to acids and bases, but it looks exactly like a double replacement reaction. And it's just like this. We have a strong acid, which, remember I talked about, that means it's going to completely dissociate, completely dissolve and break apart. And a strong base, same thing, it's going to completely dissolve and break apart, are going to be mixed together in an aqueous solution and produce an ionic salt. Remember, that's just a salt or an ionic compound, and water. The reason this is a double replacement reaction is because our hydrogen and our whatever is attached to our base are going to swap places. So you can see we have our acid. This is our example of our acid with a hydrogen at the front and some anion attached to it, plus our base, which is going to have a cation and a hydroxide ion attached to it. Those are all going to dissociate because they're aqueous, and our cation and anion are going to come together to form an ionic salt. Will come together. They're still aqueous, so they're dissolved. But this is our double replacement reaction. And our hydrogen and our hydroxide will come together to actually form water. So I know that way back in the beginning of the semester, we looked at double replacement reactions, and often a product was, and I had you guys balance equations looking at water as HOH instead of H2O. This is why. It's because really, when we have a acid-base reaction or this type of double replacement reaction, our acid and our base are going to dissociate and come together and neutralize each other and produce water. So that is why it's called a neutralization reaction, because we are going to have our happy amount of hydrogens and hydroxides coming together just to produce water, which pure water has a pH of exactly 7. Now we're going to talk a little bit more in class about why rainwater does not have a pH of 7, why it's actually slightly acidic, and kind of what the ocean looks like, etc. You do need to be able to write an equation like this, and it's also a good review for the final. So the way that we're actually going to use this is we are going to do what's called a titration in our in the lab next week, and it's just a lab procedure to determine the molarity of an acid or base based on stoichiometry of a neutralization reaction, so some sort of double replacement reaction. And what we do is we do this reaction to what we call the end point, and the end point is shown by a color change and an indicator. I was going to bring one and show it to you, but it was just too complicated to bring it over to campus ministry. So you will see it in class next week, but this is our little drawing of that. We have basically an acid. Next week we are going to have an acid of known concentration in a beaker and this titration stuff, equipment that we're going to teach you about. And in here there's a base of unknown concentration. And basically what we do is we drip the base, drop by drop by drop, into the acid, and when there's a color change, we know that's the end point, and we know that it is neutralized and the pH is 7. And then we can use this new formula to determine what the molarity of our unknown substance was. In our case, it's the base. We don't know what the molarity of the base is. So that's the example that I'm going to do. I think so. Okay. So basically, the new formula that we are going to use is actually not that new. And it is the molarity of the acid times the volume of the acid is going to be equal to the molarity of the base times the volume of the base. So you can see I put right here, I labeled these, but you need to remember this, it looks really similar to our gas law, to something in gas laws, but this M is not mass, it is molarity, and this is still volume though, okay? So remember, large M molarity. Okay, so our example is a 15 milliliter sample of a 0.250 milliliter hydrobromic acid, or you guys might just say hydrogen bromide, that is fine, is titrated to the end point. So that just means we had that color change and we stopped doing our procedure with 25.0 milliliters of potassium hydroxide. What is the concentration of the base? So Emma is working out and plugging in some of our stuff, but I just want to note what our acid and our base is and how we know, okay? So we know that this is our acid because it starts with a H, a hydrogen, and so when that is dissolved, it is going to dissociate and produce hydrogen ions. We know this potassium hydroxide is our base because there is a hydroxide ion attached to the end of it, and it is going to produce hydroxide ions when it dissociates. So the concentration is going to be equal to the molarity of the acid times the volume of the acid divided by the volume of the base, and that equals 0.150 molar potassium hydroxide. We do want to include our perfect. Can you put a box on it? Thanks. Okay. Then we have to write a balanced equation for this reaction. So what we are going to do is we are going to start with our acid. So we're going to write HBr aqueous plus KOH aqueous, and then these just swap places, and we are going to get, you can write it right down here, what do we have? HOH, liquid, because that's our water, right? Plus KBr, aqueous. Okay, so this is our ionic salt, and here's our water. That's all for today. Thanks for watching.